Good afternoon, everyone. My name is Juan Nguyen, and today I'll walk you through a credit approval modeling project I developed, not only to predict whether a credit card application should be approved, but also to do so in a way that is transparent, fair, ethical, and aligned with responsible AI principles. My goal with this work is to demonstrate how machine learning can support faster and more consistent lending decisions while addressing the governance, compliance, and reputational risk that come with automatic decision systems. From a business perspective, this is critical use case because credit approval sits at the interactions of growth and risk for every bank. If we approve too aggressively, we increase exposure to bad debt. However, if we reject too conservatively, we lose qualified customers and revenue potentials. A strong model, therefore, needs to balance the predictive performance with fairness, interpretability, and operational trust. The analysis was structured through five major components. First, how should the data be prepared so the model learns meaningful patterns? Second, which performance metrics actually matter for this business case and problem? Third, which classification models gives the best balance of predictive power and generalization? Fourth, does the model behave fairly across different applicant groups? And fifth, can I cleanly explain both overall model behavior and individual decisions? Let me start with the modeling workflow. I separated the target variable from the predictors and then split the data into training and test sets using a 75-25 split with stratification, so the class distribution remained consistent across both data sets. That decision matters because in a credit approval setting, imbalanced classes can easily produce misleading results if training test samples are not representative. For the pre-processing, I use a pipeline-based design. Numeric variables such as account length, total income, age, years employed, numbers of children, and family size were handled separately from binary and categorical variables. And my workflow applied standardization for numerical features as well as one-hot encoding and frequency encoding for categorical inputs. This approach improves the consistency and makes the modeling process more reproducible. Because every candidate model sees the data through the same structured pre-processing framework, that pre-processing choice is also supports governance. In a production setting, one of the biggest operational risks is having ad hoc transformations applied differently in training versus deployment. By embedding pre-processing directly inside the modeling pipeline, I established a controlled and auditable workflow. Now, let me address a critical methodological or procedural decision. I deliberately did not choose to use synthetic oversampling. Techniques such as SMOTE, borderline SMOTE, or even advanced neural network-based data generation methods. While these techniques are popular for handling class imbalance, they introduce synthetic data, essentially algorithmic hallucinations that can create serious data integrity issues. In a highly regulated domain like consumer lending, synthetic records pose legal, regulatory, and ethical risk. If a regulator or auditor asks us to trace a decision back to a real applicant, synthetic data cannot provide that accountability. Therefore, I handled class imbalance at the model level using tools from XGBoost, Random Forest, and GBM internal built-in class weighting and threshold calibration, ensuring that every prediction is based entirely on real applicant data. In terms of the model comparison, I focus on metric selection. I recognize that accuracy alone is not sufficient because the target is imbalanced. A model could appear strong by favoring the majority class. Instead, my evaluation emphasized precision, recall, F1 score, and ROC AUC, with ROC AUC prioritized during model selection because it measures how well a classifier separates approved and non-approved applicants across all possible thresholds. This metric strategy is appropriate for credit approval. Precision matters because we want confidence that applicants I predict as approvable are truly strong candidates. Recall matters because we do not want to miss too many qualified applicants who could have been approved. F1 score helps balance those two objectives, and ROC AUC gives us a threshold independent view of ranking quality. After defining the metrics, I compared the multiple classification models rather than jumping straight into one algorithm. I evaluated logistic regression, regularized decision tree, random forest, XGBoost, and His gradient boosting model, a variant of GBM. That comparison is important because it demonstrates the final choice was evidence-based rather than preference-based. There's also a business reason for comparing both simple and complex models. Logistic regressions provide a clear benchmark and it is very easy to interpret, while tree-based ensemble methods can capture nonlinear patterns and interactions that can often be present in real lending data. By testing across that spectrum, I gain a better view of the trade-off between simplicity, predictive power, and governance complexity. Once the candidate models were trained, I evaluated model fit and generalization using learning curves. I applied learning curves analysis across all models and later generated a learning curve again for the selected XGBoost pipeline using F1 score as the evaluation metric for threshold fine-tuning. That step is critical because a high-performing model on a single split is not enough. I also need evidence that performance remains stable as training size changes. Learning curves helps answer two questions executives should care about. First is the model overfitting, meaning it performs well in development but may fail in production. Second is the model underfitting, meaning it is too weak to capture underlying approval patterns. By including learning curves analysis, I moved beyond simple leaderboard thinking into a model risk management. After comparing the models, I selected a tuned XGBoost classifier as my final model. After further experimenting with multiple algorithms, the Tune XGBoost classifier was chosen as the optimal model, and I calibrated that decision threshold to 0.45. That threshold tuning matters because the default zero point 0.5 cutoff is not always the best business decision rule when the cost of false approvals and false denials is asymmetric. In other words, I did not choose this model because it was powerful. I chose it because it offered the best overall balance of discrimination, threshold flexibility, and business usefulness after structured comparison and tuning. That is the kind of disciplined model selection process financial institutions need when decisions affect customers, capital exposure, and regulatory scrutiny. Now, let me turn to the responsible AI component, which is one of the most important part for a credit risk machine learning project. The work does not stop at predictive performance. I explicitly evaluate fairness across multiple sensitive attributes using demographic parity difference and equalized odds difference. This is exactly the right decision for a credit approval use case because a model can appear accurate overall while still producing uneven outcomes across groups, violating the problem of fairness. For the logistic regression model, I found relatively fair treatment across income type with a demographic parity difference of 0.1746 and an equalized odds difference of 0.18, and across gender with a demographic parity difference of 0.19. For the XGBoost model, I observed the best fairness results on gender, where demographic parity difference is 0.09 and equalized odds difference is 0.14, and on income type, where demographic parity difference is only 0.135. The equalized odds difference is 0.219. For the GBM model, gender remained one of the better performing attributes with demographic parity difference of 0.14 and equalized odds difference of 0.17. What these results tell us is that fairness is not a binary pass or fail issue. Different models can shift bias in different ways, and a model that performs well overall can still create disparity or specific subpopulations and violations of fairness. That is why fairness evaluation is valuable. It surfaces where the model is relatively balanced and where additional mitigation may still be needed. For an executive audience, the key message is fairness evaluation is a risk control, not just a technical add-on. It helps reduce the chances of regulatory challenges, customer complaints, and reputational damage associated with inconsistent or discriminatory lending outcomes. It also creates a stronger basis for governance because the institution can document that bias was measured rather than ignored. The next question is explainability. In highly regulated decision environments like lending, alone is never enough. Leaders need to understand what is driving model behavior. I address this through both global and local explainability methods, which is exactly the right structure for a responsible deployment framework on an issue of credit risk. For global explainability, I generated partial dependency plots for several top numerical variables, including account length, number of children, age, total income, number of family member, and years employed. These plots isolate the marginal effect of individual features on predicted approval probability. This helps leadership understand not just which variables matter, but how changes in those variables shift the model's prediction. I then extended global interpretability with a SHAP B-swarm analysis for the tuned XGB boost model. The SHAP B-swarm's plot provided both the direction and distribution of feature impact across the applicant population rather than only a magnitude of ranking. Account length emerged as the dominant driver in the model's decision making. That matters from a business and a compliance standpoint. A global explanation helped confirm whether the model is learning patterns that are reasonable and policy aligned rather than arbitrary or suspicious. They might also make it easier to communicate model logic to non-technical stakeholders, such as compliance leaders, internal audit, and risk committees. I also included local explainability, which is crucial in consumer finance. A SHAP waterfall analysis for an individual applicant to show how the model moved from baseline expectation to that person's final prediction. This is important for transparency, explaining why a specific person was approved or denied, and connects that capability directly to responsible AI and regulatory compliance. This is one of the most practical parts of the whole workflow. Global explanations tell us how the model behaves overall, but local explanation answer the real stakeholder question: why did this person get this decision? That level of transparency is essential if an institution wants a model that can be defended internally and externally. I went one step further by including counterfactual interventions. While SHAP values explain why an applicant was approved or denied, counterfactual explanations provide actionable recourse by showing what would need to change for a denied applicant to receive an approval. That is powerful capability because it turns a model from a black box gatekeeper into a decision support tool that can also guide customer-facing recommendation. From an executive perspective, counterfactuals create business values in two ways. First, they improve transparency and perceive fairness by showing that decisions are not arbitrary. Second, they support the more constructive customer engagement by identifying modifiable factors linked to approval outcomes. If I were to summarize the strategic takeaway from my project, it would be this. The strongest machine learning solution is not simply the most accurate one. It is the one that combines strong predictive performance with stable generalization, fairness monitoring, and explainability at both the portfolio and applicant levels. This is the standard that should be deployed in an extremely regulated industry. In terms of business impact, my final recommendation is to view the tuned XGB Boost model as a strong candidate for deployment, but only within a governed, responsible AI framework. That means using the model with ongoing fairness, monitoring, documented threshold governance, explainability artifacts for oversight, and periodic review as applicant behavior and portfolio composition evolve. In other words, the model should be treated as a managed decision system, not a one-time technical output. For the CEO, the value is improved decision speed and scalable growth. For the chief risk officer, the value is better balance between approval quality and risk exposure. For the CTO or CDO, the value is a reproducible pipeline with explainability and monitoring hooks. And for the chief compliance officer, the value is stronger evidence that the institution is taking fairness, transparency, and accountable AI seriously. Thank you for your time. I have demonstrated that it is possible to build a credit approval model that is not only high performing, but also explainable, fairness aware, ethical, and more suitable for responsible real world use. Thank you very much.